Hello everyone, this lecture is to introduce community cyber infrastructure for ecological forecasting. We have already known the three elements toward realistic ecological forecasting: select the model structure to represent the real-world processes, constrain parameter uncertainty through data simulation, and generate external forcing, which represents the future climate conditions. A data model self-consistent system is required to automate the workflow. An example is EcoPad. The software system links real-time forcing to ecological forecasting. It's designed to facilitate communications between field experimenters and modelers to gain best science. A web-based graphic interface is provided to interact with EcoPad. Therefore, it's easy to access and operate the system. Once users make a request, EcoPad will execute the tasks integrated, such as model simulation, data assimilation, and forecasting. We will learn more in the practice session. We may be curious how to set up EcoPad for our own study site or use a different model. Traditional cyber infrastructure with a new model comes with specific technical barriers for users. Tackling these technical issues leads to redundant work and inhibits sharing information across the ecological community. Actually, more community involvements will foster innovations and promote revolutionary access. A major step toward reducing these technical bottlenecks is to design community-wide cyber infrastructure. In the following, I'll introduce some challenges and solutions for building community cyber infrastructure, and I will use EcoPad as an example. We'll start from fire essentials, which represent fundable, accessible, interoperable, and reusable. For good scientific practices, both research data and software should follow the FIRE principles to allow for replicability, reproducibility, and reusability. Fundability is to assign a unique and persistent identifier to a model data research. With this identifier, users are able to access all necessary data to produce the work. GitHub is a popular repository for this purpose. Accessibility is about the software preservation to reduce the technical barriers of reproducing the results. For example, the workflow should be automated and provides users with a more intuitive interfaces to handle everything. To achieve that, the key point is abstraction. That is, standardizing the tasks and schedule them to work in a specified order, while users are hidden from the details. Interoperability is that the cyber infrastructure works seamlessly across different models. It requires consistency of data formats such as model inputs and outputs. Standardizing data formats also promotes knowledge sharing across the community. All we mentioned above is to achieve replicability and reproducibility, which is to replicate the same result data by authors or other researchers. Reusability refers to use the software or part of it for different purposes. It requires tasks involved in the cyber infrastructure isolated and modularized. A possible solution is virtualization techniques such as Docker. These schematic summarize specific challenges or requirements of building a community cyber infrastructure for general model data integration studies. These studies can be divided into 4 categories: data ingest, calibration, model into comparison, and forecasting. Data is crucial in model-relevant studies. However, it's difficult to locate and maintain data manually because their massive volume and diversity. Therefore, standards are important to make data to follow FIRE principles. Take ecological forecasting in Initiative Research Coordination Network as example. Standardized forecasting outputs facilitates intercomparison between different teams participated in this challenge. Beyond that, supporting interoperability is prerequisite to build community cyber infrastructures and develop tools to share knowledge within the community. For example, improve the dissemination of ecological forecast, make it easier for users of forecast to conduct comparative analysis across the different forecasts, and independent validations. To be specific, standards in data ingest includes consistent naming structure. You may refer to climate forecast convention for more details. Open file formats such as CSV or NetCDF. NetCDF has many advances in scientific data management. For example, NetCDF supports a multiple dimensional data structure as shown in this figure. There are also requirements for data repository. For example, datasets are versioned, citations are provided, metadata is searchable, support machine-readable API. For big data, bottleneck relies on the efficiency of interacting with high-volume, high-velocity data. Some cutting-edge software, such as cloud computing, allow users to operate on big data without download, which saves a lot of time. I'll use model inputs as an example to introduce data ingest in EcoPad. Model inputs are environmental observations collected in study sites, such as spruce. EcoPad uses script to automatically download these observations from remote server every week and conduct data field, data clean, and convert it to standardized CSV file. All these tasks are pipelined and modularized. Therefore, it's quite easy to combine data ingest with other simulation tasks in EcoPad. The second challenge is about calibration. Specifically for ecological models, is to integrate data into a model to constrain parameters, so-called data simulation. Some parameters are able to be informed directly by observations, such as turnover rate. In this case, there are some meta-analysis tools to pull data from open access databases for constraining these parameters. Other parameters are not directly measured. Bayesian approaches, such as MCMC, is often utilized to assimilate data into a model and generate posterior distributions for these parameters. Traditional Bayesian tools can't work with external black box models. Users need to modify the model source code to include the Bayesian algorithm by themselves, which creates large technical barriers. Moreover, users have to repeat such coding work when a new model comes or new observations are available. To handle these challenges, our lab developed a model-independent data simulation module, MIDA in short, to release users from coding. Furthermore, MIDA enables seamlessly linking multiple observations with different models. All these benefits facilitate use of data simulation in ecology. Besides, models calibrated for one study site may not have the same reliable performance at other sites because the environmental conditions are different. Hierarchical Bayesian calibration can allow parameters variable between size but not completely independently. Such hierarchical Bayesian tools are able to quantify ecological variability and inform the direction of model independent. Again, standardizing the calibration results will allow more audience to adopt these results for subsequent analysis. Moreover, the standardization will also foster progress in models or more advanced calibration methods. The data simulation system in EcoPad is modularized, therefore is open to different data simulation techniques. Despite estimating parameters, data simulation EcoPad can support multiple research purposes such as test the alternative ecological hypotheses through different model structures, assess information content of data size, quantify uncertainties, and so on. Then we will talk about the opportunities and challenges of cyberinfrastructure in model into comparison studies. As we all know, our system model exhibit a high degree of spread in prediction. Thus, it's crucial to assess model fidelity through model comparison. Moreover, modelers need to evaluate the model performance each time the model structure is updated. Traditional model into comparison is challenging. First, the testing requirements of different models are unique. For example, some models require biogeochemical, ecological, and biophysics fully integrated to simulate ecological control of live area. However, some models, such as land surface models, have prescribed live area. Second, it's improper to compare model results directly because some models are uncalibrated while others are not. Considering these issues, traditional model intercomparison coordinates model simulation individually. That is, each model has a unique set of configurations. Here is troubleshooting. As a result, it's hard to coordinate and repeat the model intercomparison. Furthermore, the workflow of collecting model outputs and analyzing uncertainty is not automated. Due to the cost, the experimental design and model output requires are typically kept simple. Community cyberinfrastructure largely simplified the workload to incorporate a new model or alternative model versions into model intercomparison, or MIP. Standardized model inputs and outputs and troubleshooting are embedded in the system. This figure shows the efforts to add new data, model, or analysis. The traditional approach in the top panel, where model works independently, requires efforts scale up quadratically. However, in bottom panel, community cyberinfrastructure adopts standardized data formats and share analytic tools. As a result, the effort of involving new data, new model, and analysis increase linearly. The community cyberinfrastructure has many other advantages. For example, the MIP concurrence relevant for model or cyberinfrastructure development can be fed directly back into the system. This community cyberinfrastructure also facilitates more advanced applications such as running model ensembles for ensemble prediction or studying model structure uncertainty. All these benefits mentioned above are for modelers. Data collectors can also benefit from this cyber infrastructure. Let's start from the annotations of benchmark. It's a data size used for model comparison. By standardizing the observed data size and scoring metrics by which models are evaluated, researchers gain understanding of the model's strengths and deficiencies. With community cyber infrastructure, the data collector or domain experts will no longer worry about multiple file formats or model-specific terminology, but can focus on comparing multiple models to their data and setting up persistent benchmarks. Yet it's nearly impossible for non-modelers to remember all details about the model structure and their respective strengths or weaknesses. For example, if a model performance falls below the other, non-modelers do not know which key processes play a role. Therefore, standards are recommended to characterize the model processes. The final challenge of cyber infrastructure is from forecasting. Generally, forecasting starts with the development of ecological models that is repeatedly executed to generate a forecast with a time horizon like weekly. Data acquisition is to obtain real-time observations and to compare this data with the forecast. The forecast is then updated with the observations through statistical analysis such as data simulation. The forecasting results are achieved for future analysis and communicated to policymakers for their decision-making processes. As forecasting uses more models that differ in ecological processes, the success and failures of their forecast help advance our understanding of ecological dynamics. Furthermore, the forecasting performance can guide field experimenters to refine data collection. Community cyber infrastructure can automate the forecast cycle. Modelers, data collectors, and decision makers all benefit from the system in a cost-effective way. Forecasting EcoPad is equipped with a web-based interface, which is easy to access and operate. From the web pages, users are able to select the task to execute, select the constrained parameters from previous data simulation experiments, and select settings for forecasting, such as the forecast date and treatment. The technical architecture behind the user-friendly interface is realized by a series of Docker-contained services. These services include user response, data management, task execution, which are scalable across multiple machines, and efficient scaling of the tasks. More detailed introduction is available in Huang's paper. At the end, there are some available cyber infrastructures with most analysis capabilities we mentioned before. Here is a comparison of these cyber infrastructures from the FIRE principles and the measurements for 4 common data model integration studies. The detailed introduction is available in this paper. Thanks for watching. If you have any more questions, please feel free to let me know. Thank you.